Okay, this lecture is going to be over sections 12.5 and 12.6. We're talking about superposition, standing waves, and normal modes. So the principle of superposition states that when two waves come together, they overlap. The resulting displacement at any point is obtained by vector addition of the displacements that would be caused by the two individual waves. It's a lot like a resultant in vectors, which we've studied up to this point. So when a sinusoidal wave is reflected at a stationary or free end, the original and reflected waves combine to make a standing wave. At the nodes of the standing wave, the displacement is always zero. The antinodes are the points of maximum displacement. So fixed string ends are nodes. Ends that are free to move transversely are antinodes. So standing waves on a string of length L can have only certain specified frequencies. In other words, if you're going to have a fixed spot here and a fixed spot here for the string, these are going to be the nodes. The displacement's always going to be zero. It's never going to be above or below that x-axis there. However, the areas out here that are free to vibrate can have a displacement that is not equal to zero. And the antinodes are going to be different depending on what type of wave actually results. Wherever the maximum displacement ends up, that's where it's going to be. So standing waves on a string of length L can have only certain specified frequencies. When both ends are stationary, the allowed frequencies are f of n is equal to n times v divided by 2L, or n times frequency 1. So a normal mode is a motion in which all particles on the string move sinusoidally with one of the frequencies determined from here. Each value of f of n corresponds to a different normal mode. So if n is equal to 1, then you have a fundamental frequency. In other words, it bounces totally up or down. And this is not the entire wavelength, but it's 1/2 of one wavelength. So if you see that, that's going to be considered the fundamental frequency. Now, let's say you double that. And so now the entire wavelength, as you see, can go here, then here, then here. That's the entire wavelength. N is equal to 2. And this becomes the first overtone or the second harmonic. If you go to the third harmonic, n is equal to 3, then you can see 1.5 wavelengths present there. You can see node, antinode, node, antinode, node, antinode, and then the node. Fourth harmonic, or the third overtone, would look like this. So that is something that I tend to like quite a bit. You can see here some of the descriptions of waves that arrive and then bounce back. You can see 12.11 shows the reflection of a wave pulse from an end that is held stationary and from an end that is free to move transversely. In this part of the figure, a wave pulse arrives at the end of the rope that's fastened to a rigid support. The arriving wave exerts a force on the support. The reaction to this force exerted by the support on the rope kicks it back. So you can see that the rope exerts an upward force on the wall exerts a downward force on the rope, and then the pulse inverts as it gets reflected. If you are looking at, say, a rope that is tied to a loop that is able to move, you can see as the pulse arrives, the post exerts no transverse force on the rope, and then as it gets pushed back, there is no inversion, as like what you see over here. So the conditions at the end of the rope, whether or not there's a rigid support or a complete absence of transverse force, are considered to be boundary conditions, and depending on what those are, could change the shape of this. So the formation of the reflected pulse is similar to the overlap of the two pulses traveling in opposite directions. So you can see here in figure 12.2, you've got two pulses from the same shape, but one's inverted with respect to the other, and they're traveling in opposite directions. As the pulse overlap and pass each other, the total displacement of any point is going to be the vector sum. So you can see as these two come together, you can see how that rope changes, and the shape each pulse would have on its own gets kind of blended together here, and then you can see them travel on. So that's the superposition. That's what we're talking about here. So let's say you had two pulses coming together that were both on the upper end of the rope. As they come together, boom, you get a really high peak there, and then they continue to travel on their own way. So whenever two waves overlap, the resulting displacement at any position at any time is obtained by the vector addition of the displacements of each of the two individual waves. So now let's go to section 12.6. So we're going to look a little bit more in detail about what happens when a sinusoidal transverse wave is reflected by a stationary point, like a fixed end. When the original wave combines with the reflected wave, the resulting motion no longer looks like two waves traveling in opposite directions. So instead, the string appears to be subdivided into a number of segments, as you can see here with the time exposed photographs. So let's compare that behavior with that of the waves that we studied earlier. We'll refer to those as traveling waves because when there are no reflections, they travel in one direction through the medium. In a traveling wave, the amplitude is constant and the waveform moves with a speed equal to the wave speed. For what we're examining here, the waveform remains in the same position along the string and its amplitude fluctuates. There are particular points called nodes that never move at all. Midway between the nodes are called the antinodes. And you can see those here: node, antinode, node, antinode, and then the node. Because the wave pattern doesn't appear to be moving in either direction, it is considered to be a standing wave. So here you got a string of 1/2 of a wavelength. Here's one wavelength because it goes up and then down. 1.5, and then you've got 2. A standing wave, unlike a traveling wave, does not transfer energy from one end to the other. Two waves that form a standing wave would individually carry equal amounts of power in opposite directions. There's a local flow of energy from each node to the adjacent antinodes and back, but the average rate of energy transfer is going to be 0 at every point. So let's take a look here at figure 12.15. We're going to use the superposition principle to understand the formation of a sinusoidal standing wave. The figure shows the waveform at instance 1/16 of a period, so that's how this is going to be represented. The thick pink curves, you see here, show a wave traveling to the left. You can see the arrows there. The blue shows a wave with the same propagation speed traveling to the right. The brown curve shows the resultant waveform. So at each point, the actual displacement of the string represents the vector sum of the displacements due to the two separate waves. The resultant total displacement at each node marked N is always going to be 0. Midway, the antinodes are going to be marked with A, and they have the greatest displacement. So the distance between successive nodes or between successive antinodes is going to be 1/2 of a wavelength. So node to node, antinode to antinode is going to be 1/2 of a wavelength. So normal modes. An echo of a sound wave can be produced by reflection at a rigid wall. So suppose we had two parallel walls. If we stand between the walls and produce a sharp sound pulse, then the result is a series of regularly spaced echoes caused by repeated back and forth reflection between the walls. In room acoustics, this phenomenon is called Flutter Echo, which is not something you really want. The analogous situation with transverse waves is a string with some definite length rigidly held at both ends. So if you produce a sinusoidal wave on a guitar string, the wave is reflected and re-reflected from each end. Then the waves combine to form a standing wave, like one of the waves shown in figure 1214, which I believe is like this. Both ends must be nodes, and adjacent nodes are 1/2 wavelength apart. The length of the string, therefore, has to be some integer multiple of the wavelength divided by 2. And that's where this comes from. That's the length. Now, a standing wave can exist on a string with length L held stationary only when the wavelength satisfies this equation. When we solve for the wavelength and label the possible values as follows, this is the expression, and that's what we covered there in the summary. So corresponding to the series of possible wavelengths is a series of possible frequencies. Since we knew that the frequency times the wavelength was going to be equal to the velocity, then we know that the frequency of n will represent this, because we know what the wavelength is and we know how to put it in here. So this frequency, f of sub 1, is going to be called the fundamental frequency. The others are going to be multiples of that. And so all of these values are going to be integer multiples of this. And these are going to be called harmonics, and the series is called a harmonic series. And musicians sometimes call this F2, F3, and so on as overtones. So F2 is the second harmonic or the first overtone, F3 is the third harmonic, and so forth. A normal mode is a motion in which all particles of the string move sinusoidally with the same frequency. Each of the frequencies given by equation 12.7 correspond to a possible normal mode pattern. So there are infinitely many normal modes, each with its characteristic frequency and vibration pattern. And you can see the 4 lowest frequency normal mode patterns and their associated frequencies and wavelengths. We can contrast this situation with a simpler vibrating system, the harmonic oscillator, which only has 1 normal mode and 1 characteristic frequency. So if we displace a string so that the shape is the same as the one of the normal mode patterns and then release it, it vibrates with the frequency of that mode. But when a piano string is struck or a guitar string is plucked, not only is the fundamental frequency present in the resulting vibration, but also are many overtones. This motion is therefore a combination or superposition of many normal modes. Several frequencies and motions are present simultaneously, and the displacement of any point on the string is the vector sum of the displacements associated with the individual modes. So we know what the fundamental frequency is. We know what the wave speed is. If we combine all of that, we can see that the fundamental frequency of a vibrating string with length L held at both ends is going to be this. So all string instruments are tuned to the correct frequencies by varying the tension. An increase in tension increases the wave speed and thus also increases the frequency. So because the frequency and the speed, let's see if I can find a better, frequency and the speed are directly related to each other. So the inverse dependence of frequency on length L is illustrated by long strings of the bass section of the piano and the string bass compared with the shorter strings of the piano treble and the violin. The bass strings of a piano, which make deep, low frequency notes when played, are wound with wire to increase their mass per unit length. And if you take a look at this, you can kind of see how those two are inversely related. This creates a desired low frequency without resorting to a string that is inconveniently long or flexible. In other words, you just couldn't fit it in there. So for the violin and guitar, this usually means varying the pitch. The usual means of varying the pitch is to press the strings against the fingerboard with the fingers to change the length L of the vibrating position of the string. So, as equation 12.8 shows, decreasing L increases the frequency. They're inversely related. Decrease this, brings this up. So you got some more problems there to work through.